Okay, the next subsection we're going to be looking at is the electron configuration of atoms. So here we go, the electron configuration of atoms. The goals are using the periodic table as a guide, describe the electron configurations of neutral atoms using the orbital box, SPDF, and noble gas notations. Apply the Pauli exclusion principle and Hund's rule when assigning electrons to atomic orbitals. And I want you to recall that we had a figure that looked like this for the subshell filling order. Okay, so let's take a look at writing electron configurations again. There's a third way of writing electron configurations, the noble gas configuration. So let's look at lithium as an example. Lithium has 3 electrons in it. And here, when you put these into the subshells, and I'm going to write the subshell orders down here, 1s, 2s, 2p, 3s, 3p, 3d. We're going to write that out. So when you put the electrons into these subshells, you start putting them in these subshells to the left first because they're more stable or lower energy. So when we have 3 electrons in a lithium atom, 3 electrons because it has 3 protons and therefore 3 electrons to be neutral, when we put electrons in here, we will put as many as we can into this 1s subshell as possible. Now the 1s subshell has 1 orbital and therefore we can only put 2 electrons in it. So 1s2 is what we get. So once we've filled that subshell, we move on to the next subshell. The next subshell is the 2s, and for lithium, since we have a 3rd electron, we put 1 electron into the 2s. So this is called the SPDF notation for lithium, 1s2, 2s1. Now, the orbital box diagram, we draw boxes for each of the orbitals. A 1s subshell has 1 orbital, a 2s subshell has 1 orbital. So when we put these electrons in there, we put 1 in, up, 1 down, and then 1 up. Now, why do we put 1 up and 1 down? Because the up represents a magnetic or electron spin, I should say, quantum number of +1/2, and the arrow down represents an electron spin quantum number of -1/2, because no 2 electrons can have the same set of quantum numbers. Now, if we take a look at helium for the SPDF, it's 1s2. Helium has an atomic number of 2 and 2 electrons. So we can fit both of those into the very first subshell. And the box notation looks like this. There is no noble gas notation for helium because it is a noble gas. Now, the noble gas configuration, you can actually do this for lithium. You can write helium in brackets plus 2s1. So basically, you can see this 1s2 is the same as helium. So you write helium here, and then you write down what follows the same electron configuration as helium. We could also make this into a box notation where we put helium in brackets and a box for 2s and do this. So let's take a look at another one of these as an example. Let's take a look at, say, let's see, what's after lithium, boron? Let's look at beryllium. So beryllium, which has an atomic number of 5 and therefore 5 electrons. When we take a look at the SPDF notation, we've got a 1s and we can put 2 electrons in there. We've got a 2s and we can put 2 electrons in there. And we've got a 2p and we can put 1 electron in there. Now, what does the orbital box notation look like? Well, we draw a box for the 1s subshell. We draw a box for the 2s subshell. And we draw 3 boxes for the 2p subshell, because remember, the 2p subshell has 3 orbitals. So what do these electrons look like in here? Well, when we put these in here, we put 1 up and then 1 down. For the 2s, one up, then one down. And for the 2p, we're just going to put one up right there. And this would be the box notation. So what would the noble gas notation look like if we were using the box notation? This is the same as helium. So I'd write helium for that. And then I would write this. And what would the noble gas notation look like if we were using the SPDF? It would look like this: helium 2s2, 2p1. So you show all the electrons that are beyond those that would be the same as or the noble gas. You only do this for the noble gases. So you lead with the noble gas. You would never lead with fluorine or something like that. So that's the third way of writing the electron configuration. Okay, so there's something also that we need to apply to this, and it's called Hund's rule. Hund's rule says that when assigning electrons to orbitals, you assign them to the most stable orbital first. We already know that. But if there are orbitals of the same stability, place one electron in each degenerate orbital first before pairing. So you might wonder, what is a degenerate orbital? Orbitals of the same energy. So here we have these, for carbon, we have these three subshells, 1s, 2s, and 2p. And I'm going to show you another way to show these subshells. You could do this. Here's a 1s, here's a 2s, and here's a 2p. And remember, a 1s is more stable than a 2s. A 2s is more stable than a 2p. And you can do this. So what does each line represent? Each line represents an orbital. So I could make this into an orbital box notation, but I'm not going to. Above a 2p, we would have a 3s with one orbital, then a 3p with three orbitals, and then a 3d with four orbitals, or excuse me, five orbitals. So here you can see the order of stability such that these at the bottom are more stable, and these at the top are less stable. So the filling order is such that when you put these in here, the rule is that you put them in the most stable first. So for the carbon, carbon has a Z equal to 6. So that means 6 electrons also. So you're going to put one here, and then another one here, and then one here, and then another one here. And then when you get to the 2p, you do this, but you don't pair them up first. You put them separately like that. So why do you not pair them? Well, it turns out that when you pair them, the electrons actually repel one another, and that's a destabilizing effect. Here, because these two orbitals have different orientations, those electrons are less likely to encounter one another and repel one another. Therefore, they're more stable. So you can think of these as being kids. And it's far better if you have two kids to place them in different rooms than it is to put them in one room and have them fight. So that's part of Hund's rule, is not only do you place them in the more stable orbital first, but if you have degenerate orbitals, orbitals that are the same energy, you put them in one electron to one orbital at a time before pairing. So here, if we went to oxygen, which has 8 electrons, you would do this. So watch how I fill the 2p with oxygen. I'm going to put one here. So now we have 5. Oxygen has Z equal to 8. So we have 5 here. 6, 7. So one per orbital before pairing, and then 8. And we don't like doing this, but we have to. We don't like it because the electrons repel one another if they're in the same orbital. Okay, so you might ask, well, why don't we just put one here, one here, one here, one here first? And the answer is that the difference in in subshell differences is more important than pairing. So here, you're going to fill that subshell before you move on to another subshell. But in a subshell, if you have multiple orbitals, you're going to put one per orbital before you move on. Okay, so that's Hund's rule. Okay, so let's practice what we just learned. Give the electron configuration of sulfur using the SPDF, SPDF with noble gas, and orbital box with noble gas notation. So I'm going to duplicate part of the periodic table here. So here's the 1s, here's the 2s, and here's the 3s. I'm going to need that much of the periodic table. And then here we have the 3D. And this is 1s. And this is 2p, 3p, 4p. And where is sulfur in all of this? Sulfur is right here. That's sulfur. So when we get the SPDF notation, I like to just read it directly off the periodic table. So I will go here and I start with 1s because that's the most stable orbital, or subshell, I should say. So there's a 1s. And then I count how many elements I go through the 1s on my way to sulfur. And I read just like I'm reading a book. I read the top line first, then the next line, then the next line. So here I would write 1s and then 1, 2. So I put a 2 here. And next I run into the 2s. So I write a 2s and then 1, 2. Then we have to go all the way through the 2p. And we have to go all through all 6 of them. And then we hit the 3s and we put a 2 here. And then for the 3p, we'd look at our periodic table and say, how many elements do we have to get over to get to sulfur? How many cubes? And it turns out it would be 4. So you would put 3p4, and that's the SPDF notation. So what would the SPDF with noble gas look like? Well, here, if we take a look, right here, this is what? This is a helium, so this is neon. So neon has 10 electrons in it, right? So I could write neon, and here's the first 10 electrons, and I could write 3s2, 3p4. So there's the noble gas SPDF notation. So how about the noble gas box notation? Well, we would write neon, and then for the 3s, we'd write one box for one orbital, put the 2 electrons in it. And for the 3p, we would draw 3 boxes with 4 electrons in it. And remember Hund's rule, 1, 2, 3. The first 3, each electron goes into its own orbital because that's more stable, and then 4. Okay. So let's look at this next one. Electron configurations and quantum numbers. Write the electron configuration for aluminum using SPDF and orbital box notations with the noble gas notation. So they want the SPDF and the orbital box notation with the noble gas notation. So for aluminum, I'm going to pull my periodic table out here now. And actually, you can see that we have this right here using the box notation or the block notation. So where is aluminum in all of this? Well, if we take a look in the front of our book, we'll see that aluminum is right there. So that is just above the castle wall. And that would be right here. I'm going to write in pencil. So this would be aluminum. So if we read across, we'd read 1s, 2, 2s2, 2p6, 3s2, and 3p1, because aluminum is the first element in the 3p block. So let's write that down now. So for aluminum, the SPDF, we would write 1s2, 2s2, 2p6, 3s2, and 3p1. So what would the orbital box notation look like? Well, here they're talking about, I guess, the orbital box for this. So we would write 1s, 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 1, 2, 3, Hund's rule, 4, 5, 6. So even though I know that this is going to have one up and one down in each one of them because we have 6 electrons, I'm still going to fill it using Hund's rule and put one in an orbital first before I pair them. 3s, 1, 2, and the 3p, even though we only have one electron, we're going to draw all 3 orbitals, and we're going to do that because we can see that the 3p subshell is largely empty. Now, this is the box notation. And then if we do the, let's see, noble gas, SPDF, this part is neon. So we would write neon in brackets, and then we write 3s2, 3p1. And if we did the noble gas box notation, it would look like this: neon, 3s, 2 electrons, and 3p, 1 electron. Okay, so that's the answer to that one. Now this also says, give a set of quantum numbers for each of the electrons with n equal 3. So they're talking about these 3 electrons. So let's look at these. We've got the 3s, and we've got the 3p. So let's look at the set of quantum numbers here. So we're going to look at this guy right here, and we're going to look at n, l, m sub l, and m sub s. So what's the n? It's the shell number, 3. What's l? Well, for s, l is equal to 0. What is m sub l when l is equal to 0? It has to be 0 also. And what is m sub s? Well, for the arrow going up, it's plus 1/2. What about this other guy? It's going to be similar. It's going to be a 3, 0, 0, minus 1/2. Because they're in the same orbital, they have the same set of quantum numbers for the first 3. And because of the Pauli exclusion principle, the last quantum number differs for each. Now, what is this guy going to be? Well, I already know m sub s is plus 1/2 because it's arrow up. This 3 means that it's n equal 3. P means l is equal to 1. What is m sub l? You have 3 choices. You could write -1, you could write 0, or you could write +1. It's your choice. One of those. Okay, so that's that problem. Okay, let's look at the electron configuration of the transition elements. Using the SPDF notation with the noble gas notation, give the electron configurations for technetium. So this one's kind of nice because they're saying, go ahead and start with the noble gas notation. So this says with, all right? So let me get a fresh piece of paper here. And we're looking for technetium, which is TC. Okay, so what I'm going to do here is I'm going to show you my periodic table. So there it is. We're going to zoom in on it. We're going to focus on it. And I'm going to zoom out just a little bit. Okay. And I'm going to put a piece of paper underneath it here. And let's take a look at where technetium is. So I'm going to use my dry erase pen. And here is TC right there. So we want to start reading right here at hydrogen. And that's going to be a 1s, 1, 2, 2. Next at lithium, this is 2s2. And here, remember, this is the P block. And what does the P block start with? It starts with 2p. So 2p, we have to go all the way through these 6 elements, 2p6. And then here we go down to the next period, and we've got 3s2. And then we jump across the wall, and we go all the way from aluminum through argon, which is 3p6. So here it might, oh, you can't see any of that. So this is what I have written so far. And here, when we get down to here, remember, this is 1s, 2s, 3s, 4s. So when we get here to potassium, that's 4s. And remember, this is only 2 wide, so 4s2. And then here we have 3d. Remember, this is 1s, 2s, 3s, 4s, 2p, 3p, 4p, 5p, 3d, 4d. So right here, this is going to be 3d10. And this is a little weird because here we put electrons into the 4s before we put them into the 3d. And that doesn't seem right because the 3d is more stable. But remember, this is a model for deciding where the electrons belong. And it works, okay? It works for 90% of the elements. So it's a great model, turns out. Okay, so once we get done with the 3d10, we hit gallium. So let's see, this is 2p, 3p, 4p. So gallium is 4p. So we're going to be 4p6. And then what we're going to do is we're going to jump down here to potassium. Oh, let's see. Did we already do potassium? We did. We're going to go to rubidium. And so this is 1s, 2s, 3s, 4s, 5s. So when we get to rubidium, we're going to go 5s2. So here's the 5s2. And then we go over 1, 2, 3, 4, 5 to get to technetium. And remember, this is 3D, so this is 4D, and we get 4D5. So this is the electron configuration of technetium, except it's not fully correct because we do have to put these in order of increasing energy or from more stable to less stable. So we would write 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So why am I writing the 3d before the 4s? And the answer is because 3 is more stable than 4. And then I would write 4s2, 4p6, and then 4d5 because the 4d is more stable than the 5s, and then 5s2. So this is the correct electron configuration of technetium, and this one is not. So the rule is when you're getting these electron configurations of these transition elements, you're going to have to go ahead and follow that block notation and then rearrange. That's the best way to do it. Follow the block notation, then rearrange. Okay, so let's try that again for osmium. So I'm going to erase this. And here's osmium right here. And osmium I'm going to tell you is far, far more interesting. So what I'm going to do here is I'm going to zoom out and I'm going to draw the blocks again and show you how to do osmium. So take a look at where osmium is here. So over here, I'm going to draw my periodic table. 1s, 2s, 3s, 4s, 5s, 6s, and I need to go to 7s. I think for osmium, I don't need 7s, but I'm going to go ahead and go there. And then here, I'm going to draw that. So let's fill these in. So when we fill these in, this is 1s, but then this is the p block. So we start with 2p, 3p, 4p, 5p, 6p, 7p. This is the D block, and D blocks start with 3. So S blocks start with 1, P blocks start with 2, D blocks start with 3. And then we have the mote, and the F block starts with 4. So we have 4F and 5F. Now, where's osmium in all of this? Osmium is, let's see, 1, 2, 3, 4, 5, 6. Osmium is right here, and it's 6 elements over. So let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6. So that's where osmium is. Now, this is lanthanum, which is number 57. This is hafnium, which is 72. And this is cerium, which is 58. Okay. And this over here is lutetium, I think. And that's 71. The reason I'm showing you these numbers here is because if you take a look, we go 57, 58 to 71 and back up to 72. So we have to follow that. So for osmium, here's where we start off. That's where we start off. So 1s, 1, 2, 2 elements. And then 2s, 1, 2. And then 2p. And since that's 6 wide that we have to go across on our way to osmium, it's 2p6. And then 3s, 2, 3d, 3, that's supposed to be a p. It looks like a d here because my p is drawn down on that. So it looks like a d, but that's a 3p. So I got to cross this out and write 3p6. And then we go to, after 3p, we go to this 4s. So 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then we got lanthanum, which is 57, and that's going to be a 5d1. And then we have to drop down into the 4s. So 4f, 14, come back up to hafnium, and we've got 1, 2, 3, 4, 4 more in the 5d. So I'm going to cross this off and say 5d, actually not 4 more, 5 more. So 5d6, because 1, 2, 3, 4, 5, 6. So that 5d1 for lanthanum now becomes 5d6. So here's the electron configuration. And if I rewrite it all in correct order, it would look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 4f14, 5s2, 5p6, 5d6, and then 6s2. So this would be the correct order right here. Now, suppose we wanted to do the noble gas notation. We would start right here. So what noble gas is that? Well, this is neon, this is argon, or no, this is helium, neon, argon, krypton, and I think this is xenon. So I'll double check, and yep, that's xenon. So if we start here at xenon, we could write xenon, and then 6s2, 5d1, 4f14, and then we come back up here and we get these other 5ds. So I'm going to write them separately here. So 5d5. So we want to combine these together and rearrange things. So we would get xenon, 4f14, 5d6, 6s2, and that would be osmium. Okay, so it's a pretty challenging one. And what you want to do is you want to see if you can do this for osmium on your own and get the same electron configuration as did I. Okay, so that's osmium. Now, let's take a look at some additional problems here. So, write the electron configurations for phosphorus and chlorine using both SPDF notation and orbital box diagrams. So I'm going back to this, and we're looking at phosphorus and chlorine. And this also says describe the relationship between each atom's electron configuration and its position in the periodic table. So for phosphorus, we're looking at 1s2, 2s2, 2p6, 3s2, and phosphorus is down here in the 3p. And if we look here at my periodic table, it's over 3 elements, right? So that would be 3p, 3. The box notation, I'm going to do the noble gas box notation. So that would be neon. And we would have 3s2 and 3p3. And if we look at chlorine, it would be 1s2, 2s2, 2p6, 3s2, 3p5, and we would have neon, 3s2, and we would have 3p, 1, 2, 3, 4, 5. So describe the relationship between each atom's electron configuration and its position in the periodic table. What I would say is that they're both in period 3. They're both in the 3p subshell or 3p part of the p block. And so therefore, their least stable electrons are in the 3rd shell, p subshell. All right, so that's that one. Now, using SPDF notation, write electron configurations for atoms of chromium and iron, 2 of the major components of stainless steel. You know what? We've already done examples like these. I'm going to let you try those on your own. This is a far more interesting question here. And I've already told you how to get the answer to this. So let's see if you can figure it out. So when we read through this, we see that the electron configuration of some elements Some elements do not follow the block method completely. So they follow it for the most part, but not completely. So the question here is, this is one of those elements that doesn't follow it completely. We get 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Now, this is after it's been rearranged. Before it was rearranged, we would have gotten 1s2, 2s2, 2p6, 3s2, and we would have gotten 3p6 and 4s1, 3d10. So this is what we would have had before rearrangement. But we would not predict this from the periodic table, not using the block notation. So here, what element is this that is weird, where this should be a 4s2 before you start making a 3d10? What is this element? How do we do this? I'll let you think about that for about a minute and hit pause, think about it, see if you can figure out what element it is, and then hit play. Welcome back. Did you figure it out? It's copper. How do we know this is copper? And the answer is really simple. This has 2 plus 2 plus 6, 10 electrons. Another 10 here for 20. 6 plus 2 plus 1 is 9, so that's a total of 29 electrons. Well, it's got 29 electrons, therefore how many protons? 29. So what element on the periodic table has 29 protons? Copper. So we can figure out the identity of an element just by adding the electrons together and figuring out, oh, okay, the atomic number must be this, and therefore it's this. So what other elements behave weirdly like this copper? So copper is kind of weird. What other elements would you expect to have similar irregularities? And the answer is all of these elements in that group, because elements in a group have the same chemical behavior. And the electron configuration is actually a chemical behavior. Okay, so that's an interesting question. Okay, so let's see. I think this might be a next section here. Oh, no, this is another problem. So this is a pretty long section with a whole lot of problems. And it looks like we have one more problem here that we'll go ahead and take a look at. I'm getting some scratch paper. So here, what is the maximum? This is kind of a review on those quantum numbers. What is the maximum number of electrons that can be identified with each of the following sets of quantum numbers? If none, explain. So for A, maximum number of electrons, well, when m sub L is equal to 1, we're talking about 2 electrons, because m sub S can be plus 1/2 or m sub S can be minus 1/2. So that's just 2 electrons. How about B? Well, B, we're talking about 1 electron, because we're given a set of quantum numbers where you actually have all of the quantum numbers. So we're talking about 1 electron. So basically, if you have the first 3 quantum numbers, you're talking 2 electrons. If you have all 4, you're talking 1 electron. Now, one thing I didn't check to see is, are these sets of numbers okay? And the answer is yeah. So if n is equal to 4, can L be 1 less than 4? Absolutely. If L is equal to 4, can m sub L be 1? Yeah, m sub L can actually be -3, -2, -1, 0, 1, 2, or 3. Likewise, B is okay. Let's look at C. The answer for C is none, and that's because n cannot equal L, and that's what we have. So how about, well, that's that. And the last question we have for this section, the last practice question is, depict the electron configuration for magnesium using the orbital box diagram and noble gas configuration, and give a complete set of 4 quantum numbers for each of the electrons beneath or beyond those of the preceding noble gas. So for magnesium, we have 1s2, and I'm going to cross that off and circle magnesium. Magnesium is an element that's pretty close to the top of the periodic table, so this shouldn't be too hard. So 1s2, 2s2, 2p6, 3s2, and that's it. If we take a look, that's 12 electrons, and if we take a look at the atomic number, that's 12, so we're done. What is the orbital box diagram and noble gas configuration? So the orbital box would be 1s2, 2s2, 2p6, 3s2. So that's magnesium. And here for these 2 electrons in the 3s, we're supposed to, oh, I forgot, we're supposed to do the noble gas configuration. So the noble gas configuration would be neon, 3s2, or neon, 3s with 2 electrons, spin up, spin down. And what are the quantum numbers for these? Here we would have 3, 0, 0, plus 1/2. And here you would have 3, 0, 0, minus 1/2. So for these electron configurations, you should practice doing various ones of these. But what I would do is basically try and do the electron configurations of, say, boron, aluminum, gallium, indium, thallium, and just go nihonium. Just go through this particular group till you get to thallium. That's good enough, and see if you can get the noble gas configuration, or see if you can get the electron configurations. When you get to the ones that are a little larger, go for the noble gas configuration. Okay, that will be the end of this section, and we hope to see you soon. Bye-bye.